Polymers. What is a polymer? A polymer is basically a long chain of repeating organic units which are known as monomers. To make a polymer, all you need is a molecule which can easily bond to another identical molecule at 2 points. In general, the polymers I will be focusing on undergo production with the help of axo-Nobel organic peroxides in polyethylene and persulfates in polytetrafluoroethylene through the process of free radical polymerization. This sees the 3 steps, initiation, propagation, and termination, take place to produce a polymer. Initiation, the first step, sees that when the organic peroxide is heated, with high-density polyethylene being heated at 200 degrees Celsius and low-density polyethylene heated at 100 to 170 degrees Celsius, and polytetrafluoroethylene heated at 700 degrees Celsius, it breaks apart into 2 radicals. A catalyst in the reaction helps to speed up the process, with low-density polyethylene having a peroxide catalyst and high-density polyethylene having a catalyst made from a mixture of titanium chloride and trialkyl aluminium. From this, the process of making the polymer is started, and the free radicals open the double bond in an ethylene molecule, which then forces a new radical to attach to another ethylene molecule, the process continuing forming long chains of repeating molecules. This second step is known as propagation. The third and final step is the termination. The addition polymerization process stops when the last radical on the chain meets another chain with a free radical, which is where they then combine and the process is finished, resulting in a polymer. This brings us to polyethylene. Now, so we're clear, whilst polyethylene has an ene on the end of its name, it isn't actually an alkene. This is because, through the process just described, the double bonds are broken and continuously form new sigma bonds, and as you can see here, keeps bonding with ethenes, until eventually the chain stops and there are only single bonds left. Now we've talked about polymers and how polyethylene is formed, but what are its properties and what is it actually used for? I will be talking about high-density polyethylene and low-density polyethylene, both incredibly useful and also very, very different. Low-density polyethylene and high-density polyethylene can be contrasted through their chemical structure. Low-density polyethylene is referred to as atactic, meaning its structure is distorted. This is because there are many side chains of 2 to 4 carbon atoms which branch off the original carbon backbone, leading to irregular packing and low crystallinity. This then explains the low density of the structure, as well as its transparency, as larger gaps in the amorphous structure lead to it being easier to see through. Because of the branches, the polyethylene molecules are prevented from packing closely together in hard, stiff crystalline arrangements, causing both flexibility and low density, as the forces of attraction between the molecules are weaker. Low density has a melting point of around 115 degrees Celsius, lower than high density polyethylene, as the intermolecular forces are weaker, so it requires less energy to break the bonds. From this, low-density polyethylene is a softer plastic due to its molecules not being able to pack tightly together. It is useful for sandwich bags, cling wrap, and squeeze bottles. Its flexibility allows for the plastic to fold over sandwiches and accommodate for food storage. It is also very useful for these products as it's transparent as a result of being amorphous, allowing for food to easily be identified in its packaging. High-density polyethylene, on the other hand, has a melting point of 135 degrees Celsius, which means that it is 20 degrees Celsius higher than low-density polyethylene and can withstand repeated temperatures of 120 degrees, allowing it to be sterilized. It also is highly crystalline due to there being less than 1 side chain per 200 carbon atoms in the main chain, which leads to regular packing as a result of the formation of longer linear chains. The lack of branches in its structure allows the polymer chains to pack closely together, which results in a dense, highly crystalline model, which is both strong and stiff. It is also less transparent as a result of the higher crystallinity, which is because the structure is more compact and doesn't have the gaps that the amorphous structure has. It also has a higher density as a result of the forces of attraction being stronger as the molecules are closer together. High-density polyethylene is a firmer plastic, making it good for water pipes, toys, bottle caps, and extrusion coating, the rigidity as a result of its isotactic structure. Its high level of crystallinity means it isn't able to be utilized in transparent products like sandwich bags, making it better for the use of piping and bottle caps, as well as children's toys, which are then often colored. High-density polyethylene can also withstand excessive exposure to 120 degrees Celsius, making it good for sturdier items that need to be sterilized. Polytetrafluoroethylene. Polytetrafluoroethylene forms when you swap all the hydrogens for fluorines, making it tetrafluoroethylene. Tetra meaning the 4 fluorines present here. And when polymerized from that, becomes polytetrafluoroethylene. Now this has a similar process as polyethylene, where the double bond is constantly broken and bonds to a new set of tetrafluoroethylene, allowing the chain to continue to get longer. Polytetrafluoroethylene is also known as Teflon, the non-stick surface in pans. Now, because of fluorine's high electronegativity, it holds onto its electrons so tightly and is satisfied in the polymerized chain, which makes the electrons unable to essentially break free of their connection. This is what makes polytetrafluoroethylene so strong. Polytetrafluoroethylene is water resistant due to fluorine's high electronegativity and the polarity of the carbon-fluorine bonds. It is strong and tough due to the polarity of the carbon-fluorine bonds and the dipole-dipole interaction between the chain. Polytetrafluoroethylene is also chemically inert due to the strength of the carbon-fluorine bonds, as well as being chemically resistant, as the carbon-fluorine bonds are so strong that they are too strong for other chemicals to break it, therefore also making it water and oil resistant too. It is also thermal resistant, stable between 200 to 260 degrees without degrading, and low friction, which is due to low dispersion forces. This makes polytetrafluoroethylene great for coatings of utensils, pans, and building materials. Its resistance to chemicals, water, and oil makes it a good frying pan, as it is both easy to cook and easy to clean. It is also resistant to corrosion as a result of its water repulsion, again due to fluorine's high electronegativity, and has low friction, making it the perfect coating for screws. Now, the evaluation of my models. Now, due to the obvious construction of my model made out of straws, marshmallows, and odd 3D-looking gummy bears, it clearly has its weaknesses. Neither of my models were accurate in their depiction of the 3D shape of the structures, and they both weren't to scale. In my model of polyethylene, I wasn't able to show the actual bonding of the two ethylene molecules, as I had to manually stick them together with a double bond made out of straws. The straws failed to stick to the gummy bears at all angles, not representing the bonds between the hydrogen and carbon atoms, or the double bonds between the carbon atoms, as the straws were constantly coming undone. In polytetrafluoroethylene, I wasn't able to demonstrate the electronegativity of fluorine and carbon, nor was I able to show the dipole-dipole interaction between the carbon-fluorine bond. What I was able to do, however, in both was show the difference in the double bond and the single bond through the coloured straw, which allowed for the easy understanding of the process that was occurring. This also showed where the bond moved to when the free radical was occurring. I colour-coded the hydrogen so that they were red and the fluorine so that they were blue, which again provided clarity in understanding the difference of the structures. In polytetrafluoroethylene and high-density polyethylene, I was able to show its linear structure, and in low-density polyethylene, show more of the branch structure. My model clearly demonstrated the process of initiation, propagation, and termination, as well as showing the different chemical structures and the difference between a linear and branched polymer. The different parts of the process were easily identifiable through the use of colour coding. Overall, my model was effective in showing a simplified version of the addition polymerization process and the structure of polyethylene and polytetrafluoroethylene. To conclude, the double bond and addition polymerization is the same throughout the production of both polymers mentioned, the difference being the conditions the polymer is produced under. Through the research found, the different temperature the polymers were produced at and the different catalysts affected the structure of the polymer.